my fellow assassins, to another episode of the Dark Assassins Podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. So, I'm not sure about you guys where you live, but where I live, we are in that time of year where the weather can't decide what season it wants to be, so you'll go outside in the morning and it'll be like wintertime, below freezing, and then by the afternoon you're wearing shorts because it's that warm. This week we had a day where it started out in, I think it was in the 20s, I believe, and then by the end of the day it got up into the low to mid 60s, somewhere in there. So over probably close to like a 35-ish degree temperature swing. So that was nice. But yeah, it's that time of year where the temperature just decides it wants to be all four seasons in one day. So that's always a fun time. But let's start this episode off with our trivia question. So this week's trivia question, keeping with the operating systems theme from last week, how many versions of macOS 10 were there? So I'm not looking for macOS in general, specifically macOS 10. How many versions were there? So that is your trivia question for the week. Now, for this week's cybersecurity tip, I honestly had something completely different planned, but some things happened today as I'm recording this podcast, which I'm recording this on Thursday. So some things happened. So without any further ado, let's get into this week's cybersecurity tip. So as I kind of alluded to, I had something else planned for this week. But in lieu of Linus Tech Tips channel and his Tech Quickie channel being hacked and taken down, I figured this would be a more pressing cybersecurity tip than the one I had planned. So obviously, as I mentioned, I'm recording this episode on Thursday. The hack also occurred on Thursday morning. So at least as of the recording right now, it's not all the details are super clear at this point. It's kind of some speculation on exactly what happened. So who knows, maybe by the time this episode comes out, you guys will know more than I do. But at least as of the recording of this podcast, one of the main theories kind of floating around about how the Linus Media Group, how their two YouTube channels got hacked was by some sort of session cookie hack. So basically the way that this works is somehow you get malware on your device, and then that malware is able to extract the session cookies from your web browser and then send them off to the attacker. And then once the attacker has your session cookies, they can essentially get access to all the accounts that you were logged into with those cookies. So obviously, not something good to have happen. So this week's cybersecurity tip, there's going to be some other nits and pieces thrown in here, but the main tip here is if you're not actively using an account online, make sure you log out of it when you finish. Because even if, hypothetically, you got your session cookies hacked, if you made sure to log out of all of your accounts when you were done using them, theoretically, the attacker shouldn't be able to get anything on you because you're logged out of all your accounts, so there's no active sessions for them to get into and wreck those accounts. So how the malware got on, so obviously, so assuming that this is what happened, it was a session cookie hack. Somehow someone at Linus Media Group, I'm assuming it probably wasn't Linus, but we don't have all the details yet. Someone who had access to their main YouTube channel, the Linus Tech Tips channel, and the Tech Quickie channel, somehow their account got compromised. Somehow they got malware on their system that extracted their session cookies and was able to get into those accounts and essentially change the passwords and all that good stuff and really, really mess things up. So the thing that is kind of interesting is so assuming this is what happened, of course, once the attacker was able to get the session cookie, they were able to just go to like Google and they're already logged in, and then they can go to like the account settings and change the password, change the two-factor and all that stuff, and completely lock the person out of their account and have free reign over those Linus Tech Tips channels. Now, I hear you asking, why is it that you have the ability to do all that stuff with just a session cookie? Shouldn't it be when you have to change your password or change your two-factor settings that you would have to, authenticate yourself with like at least your password? And you're right, that is actually a very excellent question. I'm glad you brought that up. And I will direct that question to Google for them to answer. Because quite honestly, I don't know why they allow you to do that, because you shouldn't be able to for instances like this. So yeah, I'm not sure, like I said, how the attacker managed to get the malware onto their computer, but somehow, assuming this is what happened, that, they did. Now, so the ways that you can prevent this from happening to you, listen to the Dark Assassins podcast, where you get cybersecurity tips every week. Jokes aside, of course, the real thing, like I mentioned, that you want to make sure you do is, while it's inconvenient to always have to log out of your account that you're signed into every single time you're done using it, or I guess you could just use like some kind of incognito mode or private browsing mode that doesn't save any of your session cookies. That would work too. But as inconvenient as it is, there's that trade-off, right? Whenever the more secure you want something to be, the less convenient it becomes. So if you want to make sure to improve the security of your accounts and make sure no session, try to prevent session hijacking like this from happening, if you make sure that when you're done using an account, you log out of it, then theoretically you should be fine. But then that comes to the second step of don't download malware on your computer, which I think that goes without saying. You shouldn't be downloading malware on your computer, but sometimes you'll get spooked. They'll get you. But some of the easiest ways to prevent you from downloading malware is, don't go to sketchy websites. But if you do find yourself on sketchy websites, don't click that big flashing neon green download button, because that's probably not legit software, I guess, is a nice way of putting it. But the other thing, as we've mentioned here on previous cybersecurity tips on the podcast, is when you're going to download software from a site, like if you get one of those sketchy emails saying that you need to update your account settings, verify that the URL that you are on is actually the URL of the organization or company or whatever of the software you're trying to download. Because there are plenty of there are plenty of links out there specifically on Google where people will pay to essentially what they'll like. OBS is a great example. So if you're not familiar, OBS is like a way that you can like do screen capture and like streaming and that kind of a thing. So one issue with OBS specifically on Google is if you type in OBS, you're going to get like these sponsored links as like the first few links. And the links they take you to are not OBS's actual website in some cases. And if you go to those websites, you'll download a copy of OBS, but there's malware, packaged in with that OBS software. So that's one thing you got to be careful. But if you just actually went to OBS's website and downloaded it directly from them and actually, put in the couple seconds to check the URL to make sure it was legit, then you wouldn't have that issue. Similarly, if you are trying to download Firefox, I think it's a pretty safe bet that if the website URL is something like xx_420 firefox_xx.com and you download a Firefox installer from there, pretty sure that's probably not going to be legit. So those are some things that you want to make sure to try to prevent this from happening to you. Now, one thing I want to bring up before we move on here is Linus did come out with a statement on Floatplane, which is their own paid for streaming type service. It's kind of like YouTube, but you pay to subscribe to the channels you want to watch, that kind of a thing. So his is what he said. He said, quote, "Regarding the YouTube channel hack, we're on top of it with Google team right now. Everything should be locked down, and we're getting to the bottom of the attack vector with the hopeful goal of hardening their security around the YouTube accounts and preventing this sort of thing from happening in the future." End quote. So he also mentioned that they were going to be planning on giving a more detailed update on their weekly WAN show, which is their kind of like weekly live stream that they do. I'm not sure if he did say it'll either be this week or the next week, I guess, depending on how quickly they can get this resolved and get their account back. But yeah, that is definitely not a good look, especially for a YouTube channel that deals in the tech space to get hacked like this. But then again, like I mentioned earlier, there's a decent chance it probably wasn't Linus's fault because Linus Media Group has, I don't even know how many people working there. I think it's I don't think it's 100 yet, but I think it's getting pretty darn close to that. So, and I have because their YouTube channels are obviously corporate, accounts, who's to say how many people have access to that account? So, it's kind of hard to say. Obviously, even they mentioned they're trying to get to the bottom of it, and they haven't figured it out yet. Which, who knows? Like I also mentioned, by the time this episode airs, could all be old news, and all this is irrelevant, and it was something completely different. Who knows? But yeah, that is going to do it for this week's cybersecurity tip. Now, as far as nerdy things for this week, I'm going to be honest. There really isn't much to report, so I'm not going to do the jingle, unfortunately. And that was really for two reasons, which I guess you could potentially argue one caused the other one. But the first reason was I just kind of felt lazy this week and didn't feel like doing anything. But the other reason was I spent way too much time on the complete waste of time that is the flagitious flaming hot pile of garbage activity which shall not be named and remain nameless. Now, those of you who have listened to the podcast for a while, you obviously know what I'm talking about. For those of you who have no idea what I'm talking about, we have a nice backlog of episodes here on the Dark Assassins podcast, And because you are listening to the Dark Assassins podcast, you are smart, so you will be able to figure it out quite quickly. Now, I also hear you saying, well, you would say that if you spent any time on said activity, and you are correct, but this was in excess. And because I spent so much time on it this week, I feel like it does not need to steal any more of my time specifically on the podcast. Now, as a matter of fact, one thing that is kind of funny about it is because I'm refusing to call it by its actual name because how much I dislike it, I've actually gotten to the point where, like, when I set reminders to make sure I do said activity, because if I didn't, I wouldn't do it because how much I dislike it, I actually have started to refer to it as garbage time. And the reason for this is because both things start with a G. So, for example, if you said activity name time, both start with G, and they're both garbage, so I figured garbage time worked pretty well. But with that said, while I might not have, tinkered around in my home lab or done any kind of scripting or programming or anything like that, I have been doing some scheming behind the scenes. And in the upcoming few episodes of the Dark Assassins podcast, over the course of, I'd say, next few weeks, month or so, there's going to be some pretty good content, I think, in the Nerdy Things section of the podcast. So you're definitely not going to want to miss that. But at least part of that content that's coming up, suffice it to say that my bank account is not too happy with eBay right about now. But as a teaser for some of that content that is going to be coming up here, over the past, I don't know how long, probably maybe a couple months or so, I've noticed that when I boot up my hypervisors, which granted, I don't do that often since most of the time they just stay running all the time because I have virtual machines and services running on them. But when I boot them up, or if I run like my Ansible scripts on them to like update my servers and they're updating and rebooting and all that good stuff, I noticed that at least the VMs kind of come to a crawl. And I noticed that on the Proxmox dashboard, the I/O delay spikes quite a bit during those times, which honestly shouldn't be that big of a surprise because I'm using spinning Rust on these hypervisors, aka hard drives, at least for the bulk storage of my virtual machines, which honestly was mistake number one. Mistake number two was the fact that on both of my main hypervisors, I'm using a RAID Z, which is equivalent to a RAID 5, but RAID Z is the ZFS version. And the reason why I say this is mistake number two is because RAID 5 and therefore RAID Z1 do not offer any kind of write speed improvement. They'll offer you some read speed improvement, but there's no write speed improvement. And the reason for this is because of the parity bit calculation that's going on behind the scenes. So unlike a striped array or a RAID 0, in those cases, you're just writing the data across all the drives and you can really maximize your write speed. Obviously, the problem being, if a drive fails, all your data is gone. Whereas if you have a RAID 5 or a RAID Z1 in this case, you can lose a drive and you can rebuild that array because of how the parity data is calculated. But because it has to write that parity data as it's writing the data to the disks, you don't get any kind of speed improvement because of that. So that was problem number two. So, yeah. But as I was trying to look for a solution for this, I was browsing around on eBay, and I noticed something quite peculiar. What the heck, guys, is going on with enterprise SSDs right now, specifically SATA SSDs? What the heck is going on? Because I came across multiple listings for essentially 2 terabytes. It was technically 1.92, but I mean, close to 2 terabytes, so I'm just going to say 2 terabytes for the sake of this. 2 terabyte SSDs for less than $70. Yes, that's right. 2 terabyte enterprise grade SSDs fully working for less than $70. And I was like, what? How? Because you can go on, other sites like Amazon, Newegg, or Best Buy, or anywhere you can buy SSDs, and you'll easily find consumer grade SATA SSDs for less capacity than basically 2 terabytes for way more than $70. So I don't know what's going on there, but yeah. So that is your teaser for one of the things that is coming up in the next few weeks. So make sure that you are subscribed to the Dark Assassins podcast so you don't miss those episodes when they drop. But eBay is also a very wild place. Also, this is completely unrelated. We're going to talk about Mac Minis here for a second. I did not buy a Mac Mini, so if that's what you were thinking, go back to the drawing board. But it's a wild place because on the one hand, right, you have these enterprise drives that are dirt cheap for how much storage you're getting. But then on the other hand, you have M1 Mac Minis, which are on par with, or in a decent amount of cases, more expensive than Apple refurbished M1 Mac Minis with the same specs. Now, how in the world does that make any sense? So, for example, here's an example. So on Apple refurbished, so this is for the base model. So the base model M1 chip with the 8 gigs of RAM and 256 gigs of storage. So Apple, on their Apple refurbished, was selling this for $469. Nice. eBay, there were sellers selling it for $500, $450, and then there were some others kind of mixed in there. So how these eBay sellers, or why people would pay, $500 on eBay when they could just get it from Apple refurbished, or heck, even $450 on eBay. I mean, yeah, sure, you're saving, what's that, $20, but at the same time, if you buy it on Apple refurbished, you get literally it's technically used, but for all intents and purposes, it's a brand new computer, since they basically make sure all the components are new and it's not scuffed up or scratched or anything like that. So you're essentially basically getting a new computer with a full 1-year warranty from Apple and all that good stuff, which in my opinion is probably worth at least $20. So there's that. And then there's the 512 gigs of storage and 8 gig model. Apple refurbished was selling that for $639. And here are some of the listings that I saw on eBay for the same spec machine. There was one going for $800, which they're out of their mind, although to their credit, there is Apple Care on that system for another 7 months, but as I mentioned, you could just buy the Apple refurbished one and you'd get a full year warranty on it. So hard to say if that's really worth it. And then there was a 651, one going for $725, and then there was one going for $820, which is absolutely ludicrous to me. Because honestly, here's the thing, guys. at that point, if you're gonna spend, $700 or $800 plus on an M1 Mac Mini with 512 gigs of storage and 8 gigs of RAM, you know what you could also do? You could also buy a brand spanking new Mac Mini with 512 gigs of storage and 8 gigs of RAM for $800 or $700 with the student discount, but you also get the upgraded M2 chip, which is a way better deal than buying the last gen version for the same price, or in some cases, more. So, yeah, I really don't know what is going on with the eBay prices. I mean, they're all over the place, which is kind of the funny thing about eBay. Sometimes, you'll find great deals, and other times you'll find things that just really just have you scratching your head. But yeah, and then as far as, the range, some people, you might be thinking that I cherry picked those, which, I mean, sure, there were some that were cheaper, but not by much, just specifically in the base model case. I think there were some that were maybe like $20-$30 cheaper than what Apple Refurbished was selling. Now, granted, in the slightly higher spec model, there was more variation in that price, but I think I saw as low as like $550. But those obviously weren't nearly in as good of condition as what the Apple Refurbished one would be. So there's that. But anyway, let's get into the main topic that I wanted to cover this week, which was data structures. Now, I'm going to preface this by saying I'm not going to be covering every data structure that exists, because as the title of this podcast episode suggests, there's a lot of them. But also, there's really not enough time to get into all of them. But I guess the first thing, when you think about data structures, probably the first thing you're going to be introduced to is some kind of array list, vector, that kind of a thing, an array. That is essentially the most basic way to kind of encapsulate data and organize it, right? So for anyone wondering, why don't you just use arrays for everything? They're simple and super easy to use. Actually, you're right. You very well could use an array for all of your data structure needs, but there's actually a meme out there that describes how you'll be feeling quite perfectly, actually. And that, of course, being the bro, I'm straight up not having a good time meme, because what you'll find is while you theoretically can use an array for all your data structure needs, it is going to be a living nightmare having to essentially reorganize your entire array every single time you do an insertion, deletion, removal, popping, queuing, depending on what you're doing. You're not going to be having a fun time, let me tell you, if you plan on using an array for all of your data structure needs, which is kind of the point of data structures, is because there's so many different use cases for how to handle data, which is part of the reason why there's so many data structures. Now, here's something that probably isn't going to sound, that's probably, when I say this, it's probably not going to make any sense at all, but it's actually correct, and it'll start to make sense once I explain it. And that being, you can store more data in a dynamically linked data structure, or some kind of dynamically structured data structure, compared to an array. So if you're using a data structure like a linked list, a tree, or a graph, or something like that that's dynamically linked, you'll be able to store more data than an array, which you might be scratching your head and wondering, how is that possible? And the main way that it's possible is arrays use contiguous memory. And basically what that means is if you want to allocate, say, 128 megabytes of memory, the way that you need to do that is you need a free sector of memory of 128 megabytes worth with nothing in between it, and just a complete unallocated space, 128 megabytes worth, in order to allocate that array. So obviously, generally speaking, nowadays, you're probably never going to run into this issue, and it's never going to be a problem, and there almost will never be a situation where you're using an array causes you problems and you won't be able to store all the data, where using a dynamically linked type of data structure will allow you to store all the data. But if you're going to ever be working on some kind of microprocessor or embedded system or something with really limited resources, it might become something that you actually have to take into account when you're designing your software. So one thing that I think we should probably get into and try to make a little more sense is how, kind of going into more of this contiguous memory versus the dynamic memory. So as we kind of mentioned in a previous episode where we talked about memory management in C and C++, if you ever want to resize your array, under the hood, what the OS is doing is it's looking for another contiguous piece of memory that's big enough to accommodate your new array, right? So if you don't have enough space, then you're going to run into problems. So for example, let's say go back to that 120 megabyte example, right? And when we mentioned in that episode talking about memory management in C and C++, that basically how the array scaling generally works is by doubling itself. And the reason it does this is to try to prevent future needs to, increase, because obviously resizing the array, recopying everything takes time. And you want to mitigate that as much as possible, especially once you get, to bigger and bigger sizes, because it takes longer and longer to do. So if you needed to, say you had, 128 megabytes of data allocated and you wanted to add another element, but you didn't have the space, so you had to duplicate that array. If you only have, say, 200 megabytes on the system, well, you're not going to be able to allocate that extra space to double the array, so you're kind of out of luck. Now, generally, if you did run into that problem, there's probably something under the hood with the operating system that would still allow you to expand your array. But for the sake of argument here, you could assume that potentially maybe you might run into problems. Now, here's another example showing this off. So let's assume that you have 46 megabytes of memory for easy numbers. You have 46 megabytes of memory, and you allocate the first 32 megabytes to one program. And then after you allocate that memory, you allocate another 16 megabytes to a separate program, and then you're left with 32 megabytes of memory left that you have free. Well, actually, no, that's wrong. I read my notes wrong. Ignore that. So you allocate the 32 megabytes, you then allocate a second 16 megabytes, and then you free that first 32 megabytes that you allocated. So now you have 48 megabytes of free memory. The problem is, while you have 48 megabytes of free memory, you have 16 megabytes of memory sitting in between your two sections of freed memory. You see what I'm saying here? So if you wanted to try to allocate more than 32 megabytes of memory in an array, you wouldn't be able to do it because you don't have a free block more than 32 megabytes. So if you wanted to allocate 40 megabytes, while you technically have you have more than 40 megabytes of space free, because you have that 16 megabyte piece of allocated memory splitting your 32 megabyte chunk on the one side and the remaining memory on the other side. You're not able to fully allocate that memory. And that's because of how, memory works, how systems are designed. There's really nothing that you can do about that. Now, on the flip side, if you say allocated the 16 megabytes got allocated first, and then the 32 megabytes got allocated second, and then the 32 megabytes got freed, then you would have a contiguous 48 megabytes of space that you could then allocate, and you wouldn't have any issues allocating that 40 megabytes worth of data. On the other hand, though, if you had this same exact problem where you had the 32 megabytes free, and then you had that 16 megabytes of allocated space, and then your remaining free space, if you're using a dynamically allocated data structure, you wouldn't have this problem because you only have to allocate enough memory for what we call a node, or your individual element in whatever data structure that you're creating. Because how dynamically linked data structures work is, rather than allocating a contiguous chunk worth of memory, you only allocate the specific amount of memory you need for that individual element, and then you use a pointer to point to the next element in the data structure. So basically what this allows you to do is you could have, a collection of these elements in the data structure in that free 32 megabyte section, and then on the other side of the 16 megabyte section you can have some more, and you'll have no problem being able to access all of those. Now, I guess one thing that we should do real quick is do a little bit of a pointers recap. I'm not sure how familiar everyone is with pointers, but as a quick, super quick overview of pointers, basically all a pointer is it's a pointer to a memory address. So basically what it's doing is it doesn't really have data in it, it's just a memory address. So when your program, say, gets to it, it just goes to that memory address, and at that memory address is some other kind of data. So you could kind of think of this like an address on a map, like an address in real life. If someone gives you an address to something, they give you 123 Main Street, 25362, Sunnyvale, California. I know that's not a real address, but for the sake of argument, pretend that's a real address. You have no idea what's there. You just know that that's an address there and something is there. That's basically what a pointer is. Now, the way that we know what is there is through data types. So if you had an integer pointer, that's basically telling you, I am pointing to a memory address, and at that address is an integer. And then what that allows you to do is it allows you to pull that data and then store it in a regular integer, or do whatever you want to do with the integer that's at that memory location. And the reason why pointers are so critical and so useful is because it's not stored on the stack, which the stack is like a temporary data structure. So like when you go into if you call a function, for example, any variables you create in that function are going to be put on the stack. But once that function returns, all those variables are gone, so you don't have access to them anymore. But if you used pointers pointing to locations in memory, those pointers in memory, they're still going to exist once that function completes, so you can still have access to them later on through your program. So that's one reason why pointers are really useful. And then also, if you're doing any kind of embedded system work or dealing like directly with hardware, pointers are critical because there are certain things you need to put in specific memory locations so the hardware will do what it's supposed to do. So that's another reason why pointers are so critical. And pointers really are at the crux of any kind of like dynamically linked data structure. As I mentioned, they point to the next element in the data structure. So another thing we have to consider when we're talking about data structures is the computational complexity when it comes to how you handle your data. So for example, if you're trying to insert something, so let's go back to the array for a quick second. If you're trying to insert something into an array, assuming you have the space allocated for it, it's immediate. It's done immediately. It's you just say, array element of 2 equals this, and it's done immediately. It takes O of 1 time, as us programming nerds say, which basically means it takes 1 step to do. Now, obviously, if you have to resize your array, that's different. If you don't have the space allocated and you have to allocate new memory and stuff, as we talked about previously, that's, its own thing. Now, if you want to allocate something in a dynamically linked structure, let's take a linked list, for example. So how a linked list works is you can essentially also do this in O of 1 time, because what you can do unless you want to insert specifically into a point in the list, which then it's not O of 1 time, but assuming you just want to insert an element to the list, what you can do is, because the linked list is just elements with pointers pointing to the next list, what you can do is you take the head node or the first node in the list, and then what you can do is you can create a brand new node, make that the head, and have it point to the previous head, and you inserted an element into the list. Done deal. So that way you never have to worry about, oh no, my array's too big, I have to resize it. That's never an issue with a linked list in this case. Now, when it comes to deleting elements in an array can be kind of tricky. It's depending on how you go about doing it. Because if you say want to delete element number 5 and you have an array of, say, 10 elements, well, now you have a hole in your array. So the way you could get around this is you could shift everything down, but that's, more steps you have to do of swapping every element over to the left one, which takes computational time. And if you imagine you have a massive array and you delete the first element, everything in that array has to get shifted to the left one. And that's not going to take an insignificant amount of time if you have a massive array. Whereas if you wanted to delete an element in a linked list, all you have to do is find the element and then take the node before it and point it to the node after it, and then you free the memory and you're done. You don't have to do any swapping around, none of that. The only problem with the linked list, though, is this is one of the drawbacks of it. If you're trying to delete the last element in the linked list, you have to go through the entire linked list just to delete it. Whereas if you say wanted to delete the last element in an array, you just get the last element, delete it, you're done. So here we get back to this conundrum of every data structure has its pros and cons. It has its advantages and its drawbacks. Now on the flip side, though, another dynamically linked data structure, it would be like a binary search tree. Now, a binary search tree, it's not as fast inserting as a linked list, because as we mentioned, a linked list just inserts and it's done. It doesn't have to do any kind of, magic trickery trying to figure out where to insert it. You can implement that into a linked list, but just your standard insert just puts it at the front. But the binary search tree, how it's designed is to make sure that all the nodes to the left are less than it, and all the nodes to the right are greater than it. So when you're inserting something, you have to take that into account and make sure you're inserting it into the right place. So this will take you O log n time, which that's the mathematical terminology, I guess you want to say. But the layman term it's still pretty darn quick. So as we mentioned in a couple episodes back where we talked about anyone can make an AI, you're not special. We talked about creating an AI to guess a number in a certain range that uses a binary search and basically cuts the number in half each time till it gets to the number. So that's basically how a binary search tree operates. It starts at the head node or the tree, the top of the tree, and then it goes down through all the leaves. So if the number you're trying to insert 15 and say the top node is 30, then you go to the left, you cut out everything on the right. Say the next node is 10, then 15 is greater than 10, so then you go to the right, and then you keep cutting the number down until you find the place you want to insert it. And then similarly to the linked list, inserting is the same thing. There's a couple more pointers you have to address, but it's literally just making sure that you're pointing everything where it's supposed to be pointed to. Now, one thing you have to be careful of when dealing with these dynamically linked data structures is what's called dangling pointers. Because if you accidentally don't free a pointer once you dereference where it's pointing to and nothing can no longer access it, that memory is just sitting there allocated and won't be freed. Now, if you're using a modern language, a fancy, a bourgeoisie language that has garbage collection built in, the garbage collector will pick that up no problem. But if you're using a more Chad language like C and C++, you do not have garbage collection. So if you have a dangling pointers problem, you will quickly use up all the memory on your system. I say quickly. Probably won't be an issue, but again, we want optimized code here. We want performant code, and dangling pointers are just memory hogs. And if you're running a web browser on your machine, you already have a memory hog, so you don't need another one. So that's one thing you have to be careful of when you're creating dynamically linked data structures, is making sure that you don't have any sort of dangling pointers. Now, I guess I should also mention that almost every programming language have these types of data structures already built in to the language themselves, so you don't have to go out and create your own necessarily. But if you go through any kind of data structures computer science course, they're going to make you write your own data structures, so just something to be mindful of in that case. And going back to what we were talking about, which was inserting and removing elements from data structures, a binary search tree, similar to how inserting takes that magical O log n time, deleting is the same thing. Because if you want to delete a node, all you have to do is you start at the top, and then you check if the value is greater than or less than, and then you go to the left or right side, and then you keep going down until you find your element. And then similarly, to remove it, you basically point the thing above it to the things below it and essentially just kind of pluck it out and make sure you don't have dangling pointers. So obviously it's not the fastest, but then again, O log n time is still pretty darn quick. Now, probably one of the fastest data structures for when it comes to inserting and removing data would be the stack and queue data structures. So we mentioned stacks when it comes to the stack in regards to like your functions and stuff, and that, surprise, surprise, uses a stack data structure. And both stacks and queues have O1 time when it comes to inserting and removing elements. And the reason for this is because you can only insert and remove from one side. So you can't, like, if you have a stack, if you want to remove, say, the element in, I don't know, like the 5th spot on the stack, you have to remove all the elements before that one to remove that one. You can't just remove it. So if you want to remove an element from the stack, you have to, remove the first one, right? So, but before we talk about stacks, let's talk about queues, because I'm pretty sure everyone and their grandma's heard about a queue, right? If you've ever had to, wait in line, if you've ever been to an amusement park, grocery store, the glorious DMV, which is known for their lines, anywhere where you've had to wait in a line, you've dealt with a queue before. So a queue operates on this FIFO structure, or a first in, first out principle, where the first thing into the queue is the first thing that gets popped off the queue. So when we're talking in computer science terms, that's called like in queue and dequeue. So the in queue, you basically take the tail of the queue and you make the element you're trying to insert, you basically just point it to the tail of the queue, and then that element becomes the new tail. And then when you want to remove an element from the queue, you go to the head of the queue, and then you remove that first element, and then the head. Well, first what you'd want to do, so you don't have dangling pointers, is you would point the head to the second element in the queue, and then you would remove that first element. So that's basically how queues work. So as you can see, when you insert, it takes O1 time, it's instantaneous. And then when you remove, it's also just O1 time, instantaneous. Now, a stack is similar to a queue, except it operates on a FILO, or a first in, last out operation. And the reason this comes in, like when you're dealing with, specifically when you're like compilers are known for using stacks when it comes to like syntax stuff. So if you're wondering how your compiler can know that you're missing a parentheses, for example, it's pretty trivial using a stack. So basically what you do is anytime you see any kind of parentheses, quotation mark, curly brace, bracket, anything like that, you basically throw it onto the stack. And then if you have anything left on the stack, like at the end of a line or function or whatever, you know something's missing. So that's an easy way that stacks can be used, like in compilers. But it, like I mentioned, it's a first in, last out. So the first element you add to the queue, the stack will just keep growing up and up and up. And then you have to remove everything below it before you can get to that first element that you added onto it. But similarly to the queue, again, if you add an element, it's instantaneous, it's just one operation, and then removing an element is again just instantaneous, one operation. But like as we mentioned, there are obvious drawbacks here, because if you want to access an element in the middle of the stack, you can't do that unless you remove everything in front of it. So obviously there are some drawbacks to both stacks and queues, and you're really limited on how you can access your data. So while inserting and removing elements are very quick, how you access it is quite limited. So we've gone over a decent number of data structures here. Obviously we didn't cover all of them. We didn't cover graphs. We didn't cover all the various types of trees. We didn't really cover anything like hash tables or hash maps, dictionaries. There's a lot of stuff that we didn't cover. But the point I wanted to bring up here was why, I guess number one, why you shouldn't be using arrays for everything, because as we see here, there are some data structures that are specifically built for certain use cases that they're really good for. For example, binary search trees work hand in hand with a binary search algorithm, because a binary search algorithm really is no good if the data isn't already in some kind of sorted or organized manner, or a binary search tree. And the reason why having a binary search tree with the binary search algorithm is so good is because you don't have to worry about resorting your data every single time you add a new element, because you can just insert it into the binary search tree and it's where it should be. You can sort your data once, throw it into a binary search tree, and then every time after that you just have to insert one element after the other, and it'll be auto-magically where it should be, which obviously it's not magic at all. It's literally just a comparison. Is this greater than or less than, and going until you find where it's supposed to be. So again, when it comes to determining which data structure you should use, you first have to figure out, okay, how am I going to be using this data? How am I planning on inserting new data into it? How am I planning on accessing data in this data structure? How am I planning on removing data from the data structure? So you really have to figure out how your program is going to function and how your program is going to operate in order to figure out what data structure you should use. So if you're doing a lot of constant lookup stuff, maybe in that case you want to use something like a hash table or a hash map dictionary. They're basically all the same thing. Maybe something like that would work. And I guess we can touch on that a little bit here. So basically how these hashed tables, dictionaries in Python, basically how they work is they work on this idea of a key value pair. So there's a key and then whatever the value is. So in a way, it's kind of like an array in the sense that you can access element of this and you get back the value. So if you wanted to get the fifth element in the array, you can say array at element 5, and then you'll get that element back. And a dictionary or hash table or hash map, however you want to say it, depending on your language, how that works is you say, I want element at key, where the key is, I don't know. We're doing data structures where the key is data structure, and then you'll get out the value at that location. So basically how these work under the hood is, the short version is they run the key through some kind of hashing algorithm, and then based off that hashing algorithm, it'll provide them a memory location where that memory value is stored, and then you can just get the value out. So you don't have to worry about traversing the entire data structure. But one thing you do have to keep in mind if you're using any kind of hash map type thing is anytime you're inserting or reading data, you have to go through the operation of hashing the key value. So there is some upfront computation involved in regards to accessing that data, unlike arrays where you just say, I want element this, and you get element that. There's no hashing or anything like that involved. It's literally just an offset value when it comes to getting the data. So they also suffer from the same problem as arrays in the sense that these hash maps, dictionaries, whatever, they take up set chunks of memory in memory. So if you want if you want to add more elements to your dictionary, hash map, hash table, whatever, you have to take a larger chunk, create a larger section in memory, and allocate more space to it. It's not dynamically linked together like some of the other data structures we talked about here. So that's another thing that you have to keep in mind. Now, if say like another example is if you want to write some kind of ticketing system to determine who's next in line to be served, the queue obviously is the obvious answer there, because the first person that gets in line should be the first person that you serve. So if you build up a queue of, say, 10 people, you don't want the person that just joined the queue to be the first person you serve. Obviously, a stack is not ideal. You'll have a lot of angry customers if you use a stack rather than a queue in this case. So another potential would be, let's say you have a limited number of possible values and you know that each value is always going to be in a specific location. In this case, you could use like some kind of lookup table, but an even simpler solution could be an array, and you implement it with some kind of like enum value or something for the lookups. Now, obviously, you could there's many ways that you could implement something like this. But if you always know that, say, this one element is always going to be at this index in the array, theoretically, I guess you could make like a struct or something and do it that way. And I guess that would work too. But you could also do an array. So let's give this example. So you guys know that I enjoy myself some Pokemon. So here's a Pokemon example for you. So every Pokemon has 6 stats. They have HP, attack, defense, special attack, and special defense, and speed. So what you could do is you could have an array of integers which stores all this data for you. And because you know the attack, the value for attack in the array is always going to be in a certain spot, what you can do is you can create an enum where each enum value is set to whatever value in the array that element is, and you can essentially make like your own kind of hash table, lookup table type thing without any of the overhead of having to do any kind of hashing, because it's literally you're just dealing with numbers in an array. So if we have, that 6 elements, you can imagine that you have an enum where you have HP set to 0, attack set to 1, defense 2, and etc. I guess you could also just make them like constant ints. But for the sake of readability and usability of your code, enum's probably a better solution there. So then if you ever wanted to, say, modify the attack stat, rather than having the terribly unreadable code of saying array element of 1 equals this, where, okay, well, what is array element of 1? You can make your code more readable and say, stats. So say your array, you call it stats because we're dealing with stats. So if you say stats of attack equals this, you say, okay, now I see what you're doing. You have an array called stats, and you're getting the element that is equivalent to the attack, and you're setting it equal to this. Got it. So this way if you're dealing with enums in this case, you don't have to do any kind of searching, no hashing, no other computation is required, and that would actually be a decent implementation of using an array as your data structure and not really having to worry about it. So really, as I've mentioned a few times, when it comes to why there are so many data structures, it's because, as we've discussed here, there are many, many, many different types of problems that you could encounter when you're writing code and developing software. There are so many different instances where one kind of data structure just simply won't work in some use cases, and in other use cases it will work. So it really depends on your use case, and that's kind of the reason why there's so many data structures. Is it's kind of like, in a way, it's kind of like programming languages, I guess you could say, where certain programming languages kind of try to tailor themselves to certain types of applications. So while you technically can, while some programming language, you technically can write things that they weren't intended to be used for, you could still do that. You're not going to have necessarily the most optimal code or the most performant code as if you wrote it in a language that was designed for. So it's the same thing with data structures, right? We talked about using an array for everything. Yeah, you could, but like I said, you're going to be straight up not having a good time when you're trying to deal with them and actually implement them, because you're going to have to write so many functions to handle how all the data is being assigned. You might as well use a data structure that already does that for you and just make your life easier. So yeah, it really comes down to your use case. Every data structure has its pros and cons. There is no silver bullet data structure that this data structure is always the best and it's always better than everything else, and this is the one that you have to use every single time, because there are just some cases where one's better than the other, and you gotta weigh those pros and cons. And that's something that comes with being a software developer, right? That it comes with the territory of knowing which data structure to use based on what your program's trying to do, and trying to make the most optimal and optimized code possible to make the best program as possible, because that's what you want to do. So I think that's probably gonna wrap it up here. We obviously, I think we ran long enough. We could obviously continue going on with data structures for a heck of a lot longer. But before we go, we of course have to get back to that trivia question. And this week's trivia question was, how many versions of macOS 10 were there? And if you said 16, congratulations, you are correct. There are 16 versions of macOS 10. It started out with Cheetah, which was macOS 10.0, and ended with macOS Catalina, which was 10.15. So congratulations for all of you that got the trivia question correct, and I hope that you enjoyed this episode of the Dark Assassins podcast, and I ask that you leave it a rating and review and subscribe if you haven't done so already, because you're definitely not going to want to miss all of the plans I have for the podcast in the upcoming weeks here. I got some real good stuff in the pipeline, which I think you guys are really going to enjoy, and I think your friends and family members are also going to enjoy it. So be sure to share it with them, especially anyone that you think would want to learn about data structures or keeping themselves safe on the internet so they don't get hacked. We had some good tips in there as well. And if you have any questions about this episode, I know we talked a lot about data structures, which maybe there is something that you have a question about. Feel free to shoot me an email at contact@darkassassinsinc.com. Or if you have any questions about future topics that you want covered on the podcast, again, feel free to shoot me an email at contact@darkassassinsinc.com. Link down in the show notes below for that. And that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bool nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.